In this tutorial, I'm going to talk about the process of writing and submitting lab assignments for this class. I'll go over how to use the LC-3 editor to create an object file, which is used as input into the simulator, and then I'll talk about some of the features that the simulator provides to help with debugging. We're starting off in the Lab 1 page. In the Setup section, you can find a link to download the Lab 1 zip file here, and the simulator here. I've already gone ahead and downloaded them. Note that the simulator only works for Windows, so if you have trouble accessing a Windows device, you should talk to the TAs as soon as possible. We'll start off by extracting the Lab 1 zip file. Inside here, there's a Lab 1 folder, and then there's a lab1.bin file. This is the file you'll be writing your program in for this assignment. Before we get to that, there's also the LC-3 simulator that you download. If you double click this, it'll ask you where you want to install the simulator. I'm just picking the default location. Once you go to this directory, you'll see a couple of programs in here that we'll be using. The first one is LC-3 edit. We'll be using this to write our programs. This LC-3 edit has a text editor, and it also has the ability to generate the object files from a program you write. I'll go ahead and open the lab1.bin file. Note that this is in the path that I extracted earlier. We've given you a little bit already in the file. The first line is hex 3000, which indicates where the program should start. And the last line is hex F025, which is the magic halt instruction that we haven't talked about yet. You're going to write your code in between these two things. For this tutorial, I'm just going to write a 2's complement algorithm that we did in class, where basically you have a value in R0, and you want to store the negated value back into R0. I'll go ahead and write the program. Okay, a couple of things to note here. First of all, I have these weird semicolons and this stuff after the semicolon. That's basically a comment. Everything after the semicolon is completely ignored because this is a file that's supposed to be written in binary. And they're called comments because basically everything here is used to describe what's going on in the program. For this simple program, I just directly translated the binary into the assembly. This can be useful, but as programs get larger, it becomes increasingly more important to have comments, and the comments will be a lot more substantial than just a direct translation into the assembly. Another thing to notice, this add instruction should be adding the value 1 to R0. For this tutorial, we're going to assume that R7 has the value 1, and we'll show you how that affects the simulator. For now, we've written the program, except this is just an ASCII 1s and 0s. We need the computer, the LC-3 computer or the simulator, to basically understand our program. So we need to convert it into a format that it can understand. That's called an object file. The LC-3 edit program can generate an object file by pressing this B button. If you press it and it shows that you have 0 errors, you'll note that in the directory with the .bin file, you'll now have a .obj file. This is what we'll be using for the simulator. Okay, so let's open up the simulator now. Simulator is a little overwhelming at first, but it's not that hard when you look at the different parts. The main chunk, right here, is memory. On this side you have memory addresses, and then we have the values stored in those memory addresses here and here. This is the binary representation, and this is the hex representation. We'll ignore this for now, but as soon as we load a program, we'll see what happens. Up at the top, you have the values in the registers. This is in binary and decimal, and these are the register numbers. You'll note that the entire machine is started off with zeros. This is not what you should expect when you reset a normal computer. It could be just any arbitrary values. The simulator happens to load all zeros, but in reality the values could be anything. there's this option over here, File Randomize Machine, and this will basically just generate random values for the registers and the memory locations. This is a more realistic picture of what a computer would look like when you turn it on. We'll see how this is useful in a second. For now, you can go to File and reinitialize the machine to reset it back to zeros. So now that we've understood the simulator, we need to load our object file. Once again, this is in that path I extracted earlier. The .obj file is generated by LC-3 edit. If we load that, we'll see that some of the memory locations have changed. Hex 3000 is where our program starts. That was indicated by the first line of the program. You'll see that this binary right here is our first line of code. And from there, it's just the rest of the program. You can also see at the right side, now these values are actually meaningful. What this is doing is basically it's reading the binary and translating it into assembly. Remember, the computer is dumb and it doesn't actually know if this stuff in memory is our instructions, but it'll go ahead and try to convert it anyway. Since our program only consists of instructions, they're all correct. Okay. Now we can actually go ahead and run the program. You can do that by pressing this Run Program button. As soon as we do that, we'll see the memory has changed and the registers have changed. Basically what just happened is we ran through our program. One thing to note is this blue arrow right here is now pointing to FD79. The blue arrow is the program counter, and the program counter just marks which instruction it's currently processing. So the reason we ended up here in FD79 is because the halt instruction moves us here. You'll also notice that the register values have changed. The halt instruction also changes some of the register values. The thing is, we're trying to find the 2's complement of the value in R0, but if the halt instruction is destroying the values in R0, then how do we actually see what's going on? And the answer is something called breakpoints. Breakpoints are basically stop signs for the simulator. As soon as this blue arrow, the program counter, hits a breakpoint, it'll stop execution, or it'll pause execution. So that way, if we put a breakpoint at the halt instruction, the simulator will stop right there before actually executing the halt. This is really useful because it'll show us a snapshot of all the registers at that point in time, before the halt instruction has taken place. It's important to understand that the breakpoint is just a tool in the simulator. The program isn't actually done until it reaches the halt instruction and executes it, but placing breakpoints will help us pause and debug our programs. We can place a breakpoint just by double-clicking in this column on the very left. It puts a little stop sign thing. What we want to do is put the breakpoint at the halt instruction. We can go back to our program by typing in hex 3000 up here, and then we can double-click at this halt instruction. So that puts a breakpoint there. Now we want to restart our program. To restart it, we have to press this blue arrow, which will set the program counter to location hex 3000. It'll set it to whatever memory location is selected. Hex 3000 is the beginning of our program, so that's where we want the program counter to be. One last thing, our goal here is to find the 2's complement of what's in R0. So it would be nice to be able to put in an initial value of R0. If you double click on these registers, it'll let you set the values. We'll go ahead and just put hex FFFF, which is -1, for those of you that remember. What we expect when the program is done executing is R0 will contain the value 1. Now remember, when we were writing our program, you can see right here, we relied on the fact that R7 had a 1 in it. However, R7 here has some value from the halt. So we'll also need to set this value by double-clicking and setting it to hex 1. Now if we run our program by using this button, what we expect is that the value in R0 will be +1, and we're going to stop right here before the halt instruction actually takes place. So if we go ahead and do that, we'll see that we hit the breakpoint, and that means we haven't actually executed the halt yet. The program execution just stopped there, just paused there. And we'll note that R0 contains the correct value, the value 1. Awesome. So we're almost done. There's a couple more things that are useful. One thing is something called stepping through your code. Stepping is kind of similar to a breakpoint, except program execution pauses after every instruction instead of as soon as it hits a breakpoint. By doing this, we can see exactly how the registers are changing after each instruction. If we restart our program, this time I'll press the step over button instead of the run button. To restart, remember, you select hex 3000 and move the program counter there. Just to show you what's going on, I'm going to go ahead and remove the breakpoint. Now instead of pressing this button, I'll press this step over. The step over button will do one instruction at a time. So if I press it once, it'll just execute that single instruction. Now remember, R0 contained the value 1 after the previous execution of the program, and what we just did was we inverted it. If you invert the value 1, you get hex FFFE. We haven't added R7 yet because the program counter is at that instruction. So if we single step again, now it'll add 1, and we'll see that the 1 that we started off with in R0 has now been converted into -1. We've negated it back. Okay, so now that we've seen how the simulator kind of works, the last thing I want to talk about is how to do proper submission. If we go back to our lab1 directory, we see this obj file. We should go ahead and delete this so we just have the binary file that we had before, and then go up a directory. Now we have the lab1 folder. If you right click this and do send to compressed file, it'll create a zip file. Then you can rename this to your eid_lab1.zip and submit that file to Canvas. Okay, so that brings the tutorial to a close. There's a lot of other features in the simulator, but that should be enough to get you started with the programming workflow and enough for this assignment. We encourage you to look around some more and get comfortable with the simulator because it'll definitely come in handy for the future labs.